Hello everyone, I hope you all are doing great. We heartily welcome you all to our YouTube channel CAD CA Master. If you enjoy what you see, hit the subscribe button and turn on the notifications so you never miss an upload. I would like to take you through the agenda. You could see this is the basics of FEA. This is all you need to know. The important terminologies in FEA, likewise elastic strength, fracture, ultimate strength, and the hardness. Well, also would like to take you through the stress strain curve, different types of materials, and what is stress and different types of stresses. Let's get into this. The first thing is the terminologies. I'd like to activate the pointer. The first thing is the yield strength, what exactly it is. So very important term you need to remember. So we call it as the maximum tensile strength that the material can handle before the permanent deformation. If you consider this particular stress strain curve, so you could see this is the point where we have the elastic strength. So this is the yield point. So whatever the region you could see from 0 to this region, so the component will withstand this load and it will also come back to its original shape if you remove that particular loading condition. Okay, so this is called as yield strength. Okay, so next one is the ultimate strength. So what exactly it is? This is the stress, that is the maximum stress before the failure occurs. So let's say you can see this is the ultimate strength point where we have the deformation. So complete deformation will happen. From here the failure of the material will start. Okay. The next one is the fracture strength. So this is the value where the stress, this is the value corresponding to the stress at which the total failure occurs. So here your component will completely break. Okay, it's for a kind of brittle material. It has slight deformation. Okay, and then this is the stress strain curve for the same. So we'll see later on. I have the stress strain curve for you people for elastic materials, the plastic material as well. I'll showcase that. Yeah. The next important terminology is the stiffness. Okay, so what exactly it does is let's say how a component resists the elastic deformation when a load is applied. So if you want to just check the stiffness of the component, so whatever the load you're going to put, okay, so that should not make the component to deform. So whatever the load you're going to apply, so if it is in that limit, so that we call it as stiffness. Okay, so how stiff the component is. So stiffness is directly proportional to Young's modulus. Okay, so you just need to remember that. Next one is the hardness. So if you take a component, it's a localized deformation which we are trying to apply on the model. So we have done some testing during the final year of engineering, like some indentation test and all, right? So by using some of the ball pens, so we just try to punch the metals, the cast steel and all. Depending upon that, we check the hardness of the metals. So likewise, so this is the resistance to the localized surface, call it as the hardness. Yeah, the next one is the resilience. So what exactly it is? So this is the ability of the solid material to absorb the energy when it is elastically deformed. So if it is going to deform up to here, so whatever the deformation is happening, so it will try to absorb that. Okay, and then if you remove the loading condition, so it will again come back to its original shape. That is known as resilience. Okay, so these are the few yield strength details we have given in the megapascal. Okay, the steel, it has 448. Stainless steel we have 520. Okay, so stainless steel has the better yield strength compared to steel. Aluminum is lower, as we already know, so it's 414. So if we use the so aluminum might be lesser than this because it's aluminum alloy which has this much. The cast iron is the completely brittle component or material, we can say it's 130 megapascal. The brass 200 megapascal approx, and the copper is 70. So it's a kind of completely ductile. Okay, 70 megapascal is the max. Yep, so these are the few yield strength details. So here we can see the stainless steel is too stiff compared to other components. Let's jump into the next slide. So these are the stress strain curves. Okay, if you look at this particular diagram, so we have this curve. So this is for the brittle materials. So this is a small strain at the fracture. Okay, so this is for the brittle material. So it will come here and it will fail. You can see yield strength wherever we have it. After that, it will definitely fail for the brittle materials. So when we have the ductile material, this is how it goes. Okay, so this is a large strain, it happens and then breaks. We had done the UTM machine testing right during the final year of the mechanical engineering. So we will be having a link. It will be we will apply the tension force from both the sides, and then at the exact center there will be a necking called thinning of the metal takes place, and then finally at a certain loading condition it will break, right? So we just did that analysis to check the engineering stress and the stress strain, we can say. So that I'm going to explain in the later sessions, don't worry about that, but just remember these are the analysis we had done. So this is the stress strain curve which is going to explain everything. So you could see there is an elastic region. So this is the elastic region where whatever the load you're going to apply, if you remove the load, so it will come back to its original shape. Yeah, and then we have the proportional limit. So A to 0 to A. So this is the proportional limit. Oxla is the stress by strain. Yeah. Now elastic limit we had seen it. This is the yield point, and then this is the ultimate tensile strength. And then this is the fracture point. So from here B to E, the component is in the plastic region, so it will permanently deform from B. So before B it will retain its shape, but after elastic limit it will lose its shape. So depending upon this classification, we have the different materials, that is elastic material, plastic material, brittle materials, and the elastomers that we'll see here. So from here only in the picture you could see if the component is lying under this, we call it as elastic. So if it is crossing this, we call it as the plastic region in plastic materials. Brittle, so these are the brittle, up to here only it will come and then it will fail, brittle materials. Elastomers like the rubbers. Yeah, let's see that. So we have the different types of materials here. The first one is the isotropic material, so where we have the mechanical and thermal properties are same in all the directions, so they don't change. Okay, so we call it as the homogeneous. Yeah. Next, for example, we have the steel into account, and then we have the cast iron. It's also isotropic material, but brittle and plastic is different case, but these are under isotropic material. The glass, diamond, steel. Okay. Next, orthotropic material. So what exactly happens here is the properties, the thermal as well as the mechanical properties are unique and independent in three mutually perpendicular directions. Let's say if we take the plywood, we have the layers like sandwich. So that will have the the properties are dependent upon the orientation. Likewise, we have the rolled metals as well. Yeah. Next one is the anisotropic material, so where the mechanical properties are directional dependent. Let's say we have the wood, right? So if you take the wood and if you try to break it with the axe, it will definitely, if you take it exactly parallel to the tree, then it will definitely break in one shot. Or if you try to do it perpendicular, it won't. It is very stiff. Okay, even the cloths, okay, and the rubber, composite materials and all comes under anisotropic materials. Just remember. So we have the material non-linearities alone will come. So these are all isotropic materials. stressed materials we have it there. Yep, so this is very important thing. So material properties needed for the linear and non-linear analysis. For the static analysis, in short, if we consider, so we need Young's modulus, Poisson's ratio as more than sufficient to deal with this static analysis to find out the stress and displacement. If you want to check the mass, or if the mass is concerned there, then we utilize the density. Okay, star in the sense it is marked for the density analysis. Same thing for the linear dynamic analysis, likewise the modal, seismic and frequency analysis. We define all these factors. For the non-linear analysis, depends if you want to check the mass, we take it. Okay. Same for the non-linear analysis, we need the Young's modulus, Poisson's ratio and density. Yeah, for the non-linear material, if you take it, we need the stress strain curve also for that particular material, very important. For the fatigue analysis, we need all three plus SN curve, that is stress and number of cycles curve. So we have the FE, SAPE and Abacus, and for the different softwares we have this stress versus number of cycle curves. So there we take that and then we define the life of the material or a component, we can say. Yeah, so just remember we need Young's modulus, Poisson's ratio as well as the density, mass density into account. So Young's modulus density we had seen, right, 0.78 something, and then Poisson's ratio we had seen 0.3, 0.45. Young's modulus is 2 into e raised to 10 like that. Now we'll see the stress. What is stress? Force per unit area, right? And then if we consider the types, we have the normal stress, shear stress, principal stress and the equivalent stress. When it comes to normal stress, you could see this is the one, sigma xx, sigma yy, sigma zz are the normal stress. When it comes to shear, these, if you just leave this diagonal, so whatever you could see, these are the shear stress. Okay, now these are the stress tensor we call it. Okay, if you consider a particular plane, okay, so we have the sigma, like let's say we consider the x-plane, sigma xx, sigma xy, sigma xz. We have these three normals, okay, and it is for all the directions. Yep. Yeah, 3 normal surfaces and 9 components we have it here. So this remains the same that side as well. So if you take the mode, so positive and negative remains the same here, and then in the mode of sigma xx, sigma yy, sigma zz. So these are the normal stress, these are the shear stress. Okay, these are the tensor we call it. Okay, yeah, so this is how we just try to extract the stresses and the shear stress and the normal stress from the model. And then so how do we use it to calculate the displacement and the stress into the analysis? The first thing is the equivalent stress and the principal stress. We need to know what exactly these are. When it comes to ductile material, how they're gonna feel? So they're gonna feel at the maximum shear. Okay, so you're gonna just twist it, and when it twists, here the shear will happen, and depending upon that it will fail. When it comes to brittle material, it's about the normal stress, so it will directly fail along the normal stress. Okay, just remember these two. And then the principal stresses are solved as eigenvalue. Okay, principal stresses, and then it is used to deal with the brittle materials. So we consider the eigenvalues and then we just take that into account to solve for the brittle materials. Okay, well, so what is equivalent stress? So very important terminologies. So what exactly we do here is in the equivalent stress, so we evaluate all the stress tensors like the normal stress and the shear stress, all we include them, and then we take one equivalent stress from these all. Okay, that is known as yield stress. Okay, and then this stress value to represent the material status of the ductile materials. Let's say if you take a particular element, so if you want to cross verify all 4 nodes and then you extract all the results, and then we're going to take the equivalent stress on that particular element, not on the nodes. Okay, remember that. Next, it is used for the ductile materials. So this is just a scalar derivative of the shear strain energy as per the unit volume measured at the different points in a stress material. Okay. Well, this is about the equivalent stress and the principal stress. So in short, we use the principal stress to deal with the brittle materials, equivalent stress to deal with the ductile materials, in short. Okay. Now, so these are the types of analysis depending upon the time domain and the frequency domain. So when it comes to static, we have the loads where we apply the loads gradually, okay, with respect to time. In dynamic, so they are applied quickly. Okay, in the dynamic analysis, we have two: time domain and the frequency domain. In the time domain, we have the implicit and explicit. You could see the details here. So it is completely independent on the time step size. Okay, here it is depends on the time step. So if you define 1 second, so it will try to deal with that particular time step and it will extract the results on time and that time step. Here it is independent of the time step. So what exactly does is it will take a lot of iterations to solve, and there are so many numerical equations will be there, and then it will use the numerical method to solve it. Here for each time step it will try to extract the results. Remember that. Okay, it will try to converge the results for a particular iteration and then it will proceed. So it is taking a lot of time and it is very expensive process. So for that we don't use much, but some analysis needed for the quasi-static problem like the metal forming and the creep analysis. Okay, we use it here, and some of these static analysis we use. For this explicit we use extensively, and the dynamic like the impact, crash, drop test, everywhere. Yeah. Next, this is the difference between linear and non-linear analysis, very important. When it comes to linear analysis, okay, so there is a relationship between the load and the response. Okay, if you consider the example, let's say we have the deformation of 1 meter with respect to 10 Newton load. If you consider the displacement and the loading, so in the linear analysis, if you consider 2 meter and then the load will be 20 meter, so it is proportional. Okay, this means that linear analysis, the flexibility of the structure need to be calculated only once. Let's say we calculate the stiffness matrix only once and we invert it. Remember that, very important. So for that we just need only one cross-sectional area, and then stiffness doesn't change there. Now here in the non-linear analysis, for example, we do the stamping, crash test, rubber analysis, and the forging. What exactly we do here is, so stiffness will change for every deformation. Okay, let's say if you consider a non-linear problem, one in which the structure stiffness changes as it deforms, that we know. Okay, all physical structures exhibit the non-linear behavior. In short, each and every component or a material, whatever it is, okay, the structure, physical structure, in short, we can call, so all are non-linear in behavior. So we just consider them depending upon the requirement and the scenarios, and we do the static analysis. Okay, and then we extract the results. Now this is the force versus displacement. As I said, for the linear it is proportional. When it comes to non-linear, it will try to change. Okay, stiffness will change. So here in the non-linear analysis, stiffness is dependent upon the displacement. Okay, and the displacement, if it happens, the cross-sectional variance proportions ratio also changes, and then stiffness will also change. Okay, and then you could see what it is written here is the initial flexibility can no longer be multiplied by the applied load to calculate the spring displacement for any load here. That is obvious. Every time it changes. Okay, in nonlinear implicit analysis, the stiffness matrix of a structure has to be assembled and inverted many times during the course of the analysis. Yeah, so if it is displaced 0.5 mm, there again the Poisson's ratio changes, the cross-sectional area decreases or increases, depends upon the material, and then it will try to extract that cross-sectional area, and then it will find the stiffness matrix, and then again it solves, it inverts and solve for that. So this is what exactly the linear and non-linear. In short, to summarize, force is proportional to displacement in linear. Non-linear, it won't. They are different. Okay. Finally, to summarize, we had went through the important terminologies, like we had seen elastic strength, fracture strength, ultimate strength, stiffness, hardness, and the resilience. We had also gone through the stress strain curve, not the ascent curve, different types of materials we had seen, the stress and the types of stresses we had seen it. Yep, so if you would like to become a C engineer, or if you're a fresher, or if you're experienced, or if you want to learn different softwares, or if you have any doubts, or if you guys need support, please do contact us. We have the contact details specified. Well, that's all. Will be continued in the next session.
We heartily thank you all for watching this video. If you enjoyed this video, don't forget to hit the subscribe button and give it a thumbs up. Follow us on Facebook, LinkedIn, and Instagram for behind the scenes content and the updates. Stay curious, stay awesome, and see you again in the next video.